everyone, I'm Xiyuan from UC San Diego. Today, on behalf of my co-authors, I present our work, First Detrain, Then Attend, Rethinking Attention for Time Series Forecasting. I will start by introducing the literature and motivation of our work, then talk about how we theoretically and empirically compare different attention models. Motivated by these analyses, we propose a new method that achieves state-of-the-art forecasting performance compared with existing attention models. Transformer has been very popular for time series forecasting these days due to its ability to capture long-range dependencies. Recent works also explore learning attention in different time, Fourier, or wavelet domains. However, there is a lack of understanding on whether learning attention in one domain offers better representation ability than the other. In this work, we theoretically understand the relationships of learning attention in different domains, empirically analyze their separate advantages, and combine their empirical advantages to build a better forecasting model. We start from theoretically understanding their relationships. Under linear assumptions, time domain attention can be simplified as query key transpose value. Given the property of Fourier metrics under linear assumptions, Fourier attention has the same form as time attention. Similarly, given the property of wavelet decomposition metrics under linear assumptions, wavelet attention also has the same form as time attention. Therefore, we show that time, Fourier, and wavelet attention are equivalent given linear assumptions. However, empirically, we also apply softmax in attention as normalization. Softmax with exponential terms has a polarization effect, which increases the gap between large and small values. We show that how such effect leads to performance gaps on data with different characteristics. For data with fixed seasonality like sine waves, there exist dominant frequencies in the Fourier space. After softmax, the polarization effect further concentrates the scores on dominant frequencies, which help the model better capture seasonal information. We show on the bottom right that Fourier attention is the most sample efficient. For data with varied frequencies like alternating sine x and sine 2x, Fourier representation has both dominant and small amplitude frequencies, and the small value frequencies embed the information of varied seasonality. Fourier softmax correctly amplifies the dominant frequencies, but also neglects the small value frequencies. Wavelet attention combines multi-scale time frequency representation and provides better localized frequency information. We show on the bottom right that wavelet attention is the most sample efficient. For data with trained, dominant frequencies are mainly low frequencies. Softmax further emphasize on them and generate misleading results. As the table shows, Fourier attention has largest errors. Moreover, as attention mechanism by nature works through interpolating the context history, all these attention models fail to extrapolate linear trend well compared to a simple MLP. This motivates us to decompose time series into training seasonality and only apply attention for the seasonal part and use MLP to model the trend. We also find consistent observations on real-world datasets. Motivated by the empirical analysis, we propose train decomposition transformer, or TDformer, that first apply seasonal trend decomposition. Then we use MLP to model the trend and Fourier attention to model the seasonal part and add them together for the final prediction. We show that on multivariate forecasting benchmarks, TDformer outperforms state-of-the-art transformer models by a large margin. We also did ablation study by replacing seasonal component with time or wavelet attention, or replacing trend component with attention, and observe worse performance. We also provided qualitative comparison with state-of-the-art FedFormer. TDformer generates predictions that better preserve the trend and seasonality. In conclusion, we first proved that attention models in different domains are linearly equivalent. Due to softmax, they show empirical differences. Moreover, attention models are generally not good at generalizing trend information. Motivated by these analyses, we propose TDformer that uses MLP to model trend and Fourier attention to model seasonality and achieves state-of-the-art performance against existing attention models. Thank you for your time and attention.